I've got another problem up here on the board. Before we do this, I want to just talk a little bit about the directions and the steps that we have for solving something like this. So I'm asking us to graph this rational function. Now the book includes an 8-step process for graphing a rational function, but that's really largely a checklist for the sorts of things that you need to include. And I've really got most of that encoded here in the directions. And I will give you directions like this on any work that I ask you to submit for credit. So be sure to include all intercepts. Now you've got to remember that means x-intercepts and y-intercepts. Holes, if any, I will remind you of that because the book mentions them but doesn't really include a lot of examples with holes. And asymptotes. Now with asymptotes, we've seen two types so far. We've seen vertical asymptotes. Those are going to occur if there's a value that makes the denominator 0 but not the numerator. And we've seen horizontal asymptotes. Now there is one other type of asymptote we'll be looking at in some future examples, and that's a slant asymptote. But a function can only have one or the other. It doesn't have to have any at all, but most of our examples will. The horizontal and the slant asymptote describe the end behavior. And a function can only have one sort of end behavior on the right and one sort of end behavior on the left, so you can't have both. Okay, if you have a horizontal asymptote, you don't have a slant. If you have a slant asymptote, you don't have a horizontal asymptote. So basically, in asking you to look for asymptotes, I'm saying find the vertical asymptotes and deal with the end behavior. Okay. Now here I am asking you to check for symmetry. The book always includes that in the 8-step process. Because these problems are so long, if I don't explicitly ask you to check for symmetry, you don't need to. However, very often if something doesn't have symmetry, like the last example that we did, this would be a super quick check because you don't actually have to plug in the opposite of x for x if you can see from just plotting some points and asymptotes that there won't be symmetry. If a point or an asymptote doesn't have a mirror image, your graph can't be symmetric. Okay. So really, you'll only need to check for symmetry if it looks like it's possible that there is symmetry. And my rule is, if I want you to check, I will explicitly say so. If you can see that there's no symmetry by inspection, as we could in the last example, totally fine to say no symmetry by inspection. Okay. You got to write that, but that counts as showing your work. Okay. And then I say your graph need not be perfectly to scale, but it should be positive or negative on the appropriate intervals. Okay, the one other thing that the book always includes in its steps is if there is a horizontal asymptote, checking to see whether you cross it. That's something that I will also explicitly say if I want you to check it. Okay, so if I don't say that, you don't need to worry about it. If I do say that, you should check it. Okay. So I think these directions pretty much give you the checklist of things to check for. The one thing that I think is missing from the book's directions is what is always, for me, the first step, which is to take my function and write it with the top and the bottom in factored form. Always want to do that because that's going to make it easier to see what makes the top 0 and what makes the bottom 0. And those are really important because if the bottom is 0, I've either got a vertical asymptote or a hole. And if the top is 0, I've either got a hole or an x-intercept. A hole, remember, occurs if there's a number that makes both the top and the bottom 0 and does not make the bottom 0 once you're in lowest terms. Okay, so here in the denominator, I can see I've got a difference of 2 squares. So that's going to be x plus 3 times x minus 3. Now, my preference is to work with the things that make the denominator 0 first. Just those aren't in the domain, figure out what happens there. But it really doesn't matter what order you do things in, as long as you get everything checked off on the list. Okay. So I can see that 3 and negative 3 are going to make the denominator 0, and neither of those makes the top 0. So if the bottom is 0 and the top isn't, we're going to have a vertical asymptote. Excellent. And there won't be any holes in the graph because there aren't any numbers that make both the top and the bottom 0. This was already in lowest terms. Couldn't reduce it as we could with the previous example. Okay, so let's go ahead and find our intercepts. Okay. If I want to find the y-intercept, Remember, that's going to be 0, f of 0. If I plug in 0, I'm going to get 0 over negative 9. That's just 0. So this graph is going to pass through the origin. Now, that's both a y-intercept and an x-intercept. Do remember that it's possible to have more than one x-intercept. So just because you've got one at the origin doesn't mean you've got all of them. But if I take a look, f of x would equal 0. Remember, a fraction is 0 if the top is 0 and the bottom isn't 0. We've already determined that the bottom is 0 at plus and minus 3. The top is only 0 at 0, so that actually is the only x-intercept. Okay, so let's take a look at the end behavior. Okay, so as x goes off to infinity, or x goes off to negative infinity, and another way of saying that is just that the absolute value of x is getting really, really big. We're plugging in something big, big and positive, here big and negative. As that happens, f of x is going to look like the fraction of its lead terms. Here's a place where I want to work with the non-factored form. The lead terms would be x over x squared. I can reduce that to 1 over x. And of course, if we're going off to infinity or negative infinity, we're nowhere near 0. So I don't need to worry about the fact that I just canceled a factor of x. Even if I were concerned about that, I can still see that x isn't 0 just because it's in the denominator. So now, what does that do as we go off to infinity? Well, now we're dividing by something really, really big. If we divide by something really, really big, what happens? We get something really, really small. This is what I like to refer to as the chocolate cake principle. And this is the difference, I think, between kindergarten and college. In kindergarten, they tell you that sharing is good. By the time you get to college, you realize that if you share, you get less of something. Now, morally, it might be good, and that's a good thing for friendship. But if I have a chocolate cake and I don't share, I get to eat the whole thing. Now, if I share it with 2 people, I only get to eat half of it. If I share it with all of the students at Saddleback College, I'm getting crumbs. So when you divide by something big, you get something small. Again, this is not a moral commentary on the merits of sharing, which actually, if I think about it, can be good. But just the fact that if you share a chocolate cake with too many people, you're only getting crumbs. Okay, so this is going to be going off to 0. So I can say as x goes to infinity, f of x goes to 0, and as x goes to negative infinity, f of x goes to 0. Okay. Now, there are some questions in the homework, and this could occur on exams and quizzes as well, where I ask you to describe the end behavior using this arrow notation. If you're just graphing, as long as you figure out where the asymptote is, it's not necessary to write this notation, but I could ask you for that specifically. Okay. All right, so that's a finite number, so that tells me we have a horizontal asymptote at that height. Well, the horizontal line y equals 0 is the x-axis. If I have a horizontal asymptote at a different height, I draw it in as a dotted line. Here, it's already drawn in. What I will usually do, and this is just to help me, is I make a note that that's a horizontal asymptote. Because I always have the x-axis drawn, whether it's an asymptote or not, and when it's time for me to connect the dots, I'm going to need to remember that I have to start and end very close to that axis. Okay, so I think I've plotted all of the important points. I've got my intercepts, I've done my asymptotes, there weren't any holes in the graph, so it's time to play connect the dot. We have one dot to connect. So that tells us that we do need a little bit more information in order to be able to graph this thing. Okay. And that ties in with the fact that we need to be positive or negative on the appropriate intervals. Okay. So I want to mark off just on a number line all of the places where my function could change sign. And that's going to be where I've got an intercept or a vertical asymptote. So at -3, at 0, and at 3. Now, to the left of -3, I know I've got a vertical asymptote here and a horizontal asymptote here. So I've got to start close to the x-axis and then either curve up towards infinity or down towards -infinity. To see, I'm just going to pick a test number. So let's just pick -4. Let's see, my function, here I had it a moment ago. I kind of like to have it in factored form, because then I can say -4 would make the top negative. -4 plus 3, that would also be negative. -4 minus 4 would be negative. I would have 3 negative factors. That's going to make this negative. All right. Well, that's going to tell me that it's got to look something like this. I've got to start close to the horizontal asymptote, and I've got to either go up towards infinity, but that would require me to cross the x-axis, which I know I can't do, so then I've got the other alternative. I go down towards -infinity. Okay, between -3 and 0, let's just try -1. If I plug in -1, the top is going to be negative. -1 plus 3 is positive. -1 minus 4 is negative. So that's 2 negatives and a positive. That's going to make things positive. So I knew I had to start either up high or down low. Going to have to start up high. And I know I've got to be 0 here. So I can draw in something like so. Now, I don't know what happens after here, because I don't know whether I'm going to touch the axis and come back up or cross the axis and come back down. So I do need to pick a test point. So let's try 1. If I plug in 1, that's positive, that's positive, that's negative. 2 positives and a negative are going to give me a negative. So we are going to cross the axis and come down like so. You'll notice we just crossed our horizontal asymptote. Now here, I didn't explicitly ask you to check for that. And the reason I didn't explicitly ask for that is because I knew our asymptote was going to be the x-axis. And so we were going to be checking for intercepts anyway. So if you've got a horizontal asymptote on the x-axis, finding the intercept, you're automatically checking for places where you touch the axis, and then making sure that your graph is positive or negative on the appropriate intervals. You'll automatically be seeing whether you cross it or not as well. Okay, so let's see. To the right of 3, let's just try 4. If I plug in 4, I'm sorry, this shouldn't be x minus 4. That should be x minus 3. I miscopied that a while back. I apologize. The second factor on the bottom should be an x minus 3. Okay, so if I plug in 4, we get positive, positive, positive. All the factors are positive. It's positive, so we've got to be above the x-axis. So we'll have to start up high, and remember we've got to approach that horizontal asymptote. Okay, so our graph would look something like this. Oh, and I forgot to check for symmetry. Let's check for symmetry. Actually, it probably would have made sense to check for symmetry before I drew the graph, but that's okay. It does look like this could be symmetric. Certainly not symmetric about the y-axis, but it does look like it could be symmetric around the origin. So if I check for that, I would be plugging in the opposite of x for x. So that would give me the opposite of x over the opposite of x squared minus 9. That's going to give me just the opposite of x over x squared minus 9. Notice the denominator is the same as with f of x. The numerator is the opposite. Now I can just pull that negative sign out front and say, ooh, that's the opposite of f of x. So this is, in fact, symmetric about the origin. And actually, it's fine to do that at the end. I usually will do that after I've plotted points before I play connect the dots. But if I had gotten that we were negative over here instead of positive, I would have been able to see that there was no symmetry by inspection. So when you check things, it's really up to you. I just wouldn't make that my first step ever, because if there isn't symmetry, you can often see that by inspection once you've plotted a few points and asymptotes. If there is symmetry, you will ultimately need to plug in the opposite of x and simplify to see whether you get the same output or the opposite output.